And welcome back as we go ahead and review our next topic, which is that of parametric functions. And before we jump into a full review of that, we first need to review a terminology, and that is of relations. Well, a relation, if you don't remember, is a set of ordered pairs, x and y, of real numbers. When we graph a relation, we're simply saying that that is a set of points in the plane that corresponds to the ordered pairs relation. The x and y in this case are actually functions of a third variable t, which we refer to as our parameter. Then we can use the parametric mode of a grapher in order to obtain the graph of the function that we want. So in order to kind of kick us off here, let's just jump straight into an example here that's going to go ahead and talk about a graph of an exponential function. So here we have the, we want to describe the graph of the relation described by x equals the square root of t, y is equal to t, and of course t is greater than or equal to 0. Additionally, we want to indicate the direction in which the curve is traced, and we want to find our Cartesian equation, which if you remember, that's your standard y equals that we would normally have for a curve that contains the parameterized curve. So let's go ahead and think about this with the graph of this function. Now the best way to do that is go ahead and pull up our graphing calculator and switch this from our standard function mode into our parameterized mode. So if you, of course, are in here, we have our function mode, which is where it is by default. We're going to switch it over to parameterized. And if I go into my y equals here, I can then, of course, have a x1, y1 value. So this, of course, is referring to our x and y functions. So x is the square root of t. So let's go ahead and plug that in. So we want to do the square root of t. And we're going to then switch to our y function, which of course is simply just going to be t. Let's go ahead and give this a nice graph. And if we take a look, here is our function. Let's actually take a nice look at that. You can see how that works. If I trace this function, you can of course see we are starting at 0, 0. And as I work my way up the curve, you can kind of follow the behavior of those different variables. Now, if we want to actually go back to our question, we want to effectively describe this curve. And if you remember, when we started tracing this, the area where we started was at the origin. We started right at 0, 0. So the direction in which the curve is traced is upward. And that's starting at 0, 0. So that is, of course, our direction in which this curve is going. And we want to find our Cartesian equation for the curve that would contain it. If we go ahead and look back at this graph, if we look at this line, you can see how it kind of looks almost like x squared here. If we go ahead and, of course, trace through that, you can see we have values are kind of similar to that. In fact, as I keep moving through here, it's not necessarily exactly there, but it looks very similar to it. So how can we check to see what it actually is? And now for the second part, we want to find our Cartesian equation. So recall, if we look at our relation up here, we know that y is equal to t. And if we know that y is equal to t, we can also say that t, if we look at what x is saying, x, of course, is equal to the square root of t. Well, the square root of t squared would be the same thing as t. So this, of course, is the same thing as saying the square root of t squared. So we can, of course, say that this is the square root of t squared, which means if this is x is equal to this value having to be squared, which means that we'd have, of course, if we square one side, we got to square the other. So our y is simply just going to be x squared. And so, therefore, we can say that that relation is going to be y equals x squared for whenever we have, of course, in this case, since t was greater than 0, we're going to say that x is greater than or equal to 0 as well. All right, and so that's going to kind of get us into the meat of what we're working with today, which is the parametric curve and parametric equations. If we assume that x and y are given as functions, so x is equal to f of t and y is equal to g of t, over an interval of t values, then the set of points x and y have to equal f of t and g of t as our coordinate points, defined by the equations, which is, of course, a parametric curve. Now, the equations are parametric equations for that curve. When we look at this definition, the variable t is our parameter for that curve, and the domain A is the parameter interval. If I is a closed interval, so A is less than or equal to t, which is less than or equal to b, then our point f of a, g of a, is the initial point of the curve, and the point f of b, g of b, is the terminal point of the curve. So initial point being where it starts, terminal point being where it ends. Now the equations and the interval altogether constitute a parameterization of that curve. And we can look at this best when we start looking at things such as circles. So with circles, in the various applications that we have them, t is often going to denote something such as time, an angle, or even a distance of particles travel along the path from the starting point. In fact, parametric graphing can be used to simulate the motion of the particle. So let's look at this with another example, and this time we're going to work on graphing a circle. So here our graph of the relation is been determined by x equals 2 cosine t, y equals 2 sine t, from 0 is less than or equal to t, which is less than or equal to 2 pi. So what we need to do here is find the initial and the terminal points, if there are any, and indicate the direction in which the curve is traced. And then, of course, we want to find the Cartesian equation for a curve which contains that parameterized curve. So much like before, let's go ahead and head to our graphing calculator. And we're going to go ahead and clear out our existing functions. And what we want to do is plot in our x equation. So we have x is equal to 2 cosine of t, and y is equal to 2 sine of t. And so let's go ahead and graph that. And so you can see we now have our function here. So I'm going to hit the trace key. And you can see we are starting at the point 2, 0. So I'm just going to make a quick note of that, just so I don't forget that. So this is at 2, 0. And then let's go ahead and trace. So if I go ahead and trace this function, and I start moving through it, you can see as I press that key to move forward, we are actually kind of following this direction. In fact, if I press the other arrow key, you can see we move this way, and it doesn't move anymore. So we have a leftward direction here. So I think the best way to describe this is not as a left or right, because that's not necessarily very conducive, but to say that this is moving maybe counterclockwise. And I can, of course, keep tracing this and up until where I reach my terminal point. And it looks like there's our terminal point. Now it looks like we have a little bit of graphing rounding error here. This sometimes happens with the calculator, but this, of course, should actually be representative of 0. So our terminal point is also going to be at 2, 0. So this is our initial point. And this is our terminal. All right, and the direction in which it was traced, we said, was counterclockwise. So that gives us some good information, but what about actually going ahead and creating the equation for this? Well, the way that we can kind of think about this is by setting this up to work on eliminating out one of our variables. Now, some of you might remember that a lot of times when we deal with things like curves and circles like that, we have our root function, which is x squared plus y squared. And we can, of course, take that back into these two functions right here to go ahead and determine what is that value that we're going to have. Well, if we have a 2 cosine t squared, that should end us up with 4 cosine squared t. And if we square the 2 sine t, we should end up with 4 sine squared t. And if I look at this, I can actually make my life a lot simpler by pulling out a common factor. So I can pull this 4 out here. So I get 4 times cosine squared of t plus sine squared of t. And if you remember, there is a rule where we can make this even simpler, because what is cosine squared plus sine squared? Well, we have to remember that anytime we have something in here, and of course I can give this a variable, whether it's t or x, it doesn't really matter, we just know that that is going to equal 1. So effectively, I have here 4 times 1, which means that the value for this equation, the x squared plus y squared, is equal to 4. Now, circles, of course, are just one thing that we can use these parameterized equations for. The other thing they come in handy for are ellipses. And parameterization of ellipses are very much like the parameterization of circles. And the standard form of an ellipse centered at 0, 0 is going to be very similar. We have x squared plus y squared. But this time you notice it's x squared over a squared plus y squared over b squared, and again set equal to 1. So with that in mind, let's jump right into graphing an ellipse and see what we can come up with. So here we are graphing x equals 3 cosine t, y equals 4 sine t from 0 to less than or equal to t, less than or equal to 2 pi. And again, finding that Cartesian equation, all right, and we want to know what portion of the graph of the Cartesian equation is traced by the parametric curve, and we can also indicate the direction in the initial and terminal points, if any. So first thing we're going to do before we worry about anything else is grab our calculator. Let's go ahead and clear out the old functions here, because we don't need these anymore. And let's go ahead and put in x equals 3 cosine of t. And our second equation is 4 sine of t. All right. I'm going to actually change my window for this one. I'm going to change this to square here. And you can see that we have a kind of a nice ellipse right in here that we can take a look at. I could even zoom this in a little bit if I wanted to. But I think this is going to be good enough for it to kind of give us an idea. So let's just trace this. And you can see right now we are starting at the point 3, 0. So I'm just going to, again, write that down just so I don't forget about that. And then let's go ahead and get ready to trace this function. So if I go ahead and press the arrow key forward, you can see we are now moving along our curve. It looks like we're moving counterclockwise again. And so as I move through this, and you can see that we have now stopped. Again, looks like we have a calculator error here, but looks like our terminal point is also going to be at 3, 0. And again, just like before, when we did this function with our circle, remember we had a point where we couldn't go backwards. Same thing here. If I were to trace this the other way, we are now, of course, moving backward on our line. We will find that when we get back to that initial point, we cannot precede it, which means that is, of course, our initial point here, so 3, 0. So we know our initial and terminal points simply just from graphing this, so I'm just going to go ahead and label that right now. Even though I know that is a later part of the problem, I'm just going to go ahead and take that information out of there right away. All right. Additionally, we know the direction of the curve, all right, which we found was, again, going to be counterclockwise. Now, the big thing we need, of course, to pull out from here is the Cartesian equation. So let's use that base form that we had before, which was x squared over a squared plus y squared over b squared is equal to 1. All right, with this in mind, let's go ahead and pull in the information that we need from here. And a and b, we can actually pull from right here, because this is our a term and this is our b term. So this is our a, this is our b. Very important thing to keep in mind here. And so let's go ahead and substitute in those values. So we get x squared over 3 squared, which I could also just rewrite that. I'm actually going to make my life a little simple here. Let's actually just quantify that as one big part here. We can actually just simply say that's the same thing as x over 3 quantity squared. And we'll do the same thing here. We'll say y over 4 quantity squared. And because now these are quantity squareds, I can then go ahead and say this, since we know this is equal to 1, and we have cosine and sine here. Remember, we had previously just seen this exact same thing with our circle. So this, of course, is the same thing as cosine squared of t plus sine squared of t. But again, I don't need to worry about this part here, because again, remember, our standard form said this is equal to 1. So really, this is just extra stuff we don't really need to worry about. So our having x squared over 3 quantity squared plus y over 4 quantity squared equal to 1 should give us a good equation. Now, the last thing that we just need to answer for this question is what portion of the graph is traced by the parametric curve. And of course, that is going to be one that we have to actually think about when we look at this equation. Now for this is again going back to our a and b. So our a and b we identified as 3 and 4, x being one component and y being the other. So our major endpoints, we have a major endpoint at 0, and that's going to be plus or minus, because again, remember we have squares to deal with here. And then we have a 4, because this is our y. And our other endpoints. So these are going to be our minors because now we're dealing with the other coordinates. So let's do our minor. This is going to be a plus or minus of 3, 0. And just one other thing to note with both the circle and the ellipse here, when you're talking about counterclockwise, don't forget, and I didn't put this in the other page, to make sure that you label that this is going from 0 to 2 pi, because remember that is going to be the range here. So you of course can also put this piece right in here, but we need of course to make sure we specify when we're talking about counterclockwise so we know exactly which part of the graph we're looking at. Now the last thing really to discuss here when we're talking about parameterized functions and equations and relations, all this good stuff, is lines and other curves. So lines, line segments, and many other types of curves can also be defined parametrically. So again, very similar to what we had before, we're going to draw and identify a graph of the parametric curve determined by x equals 3t, y equals 2 minus 2t, and we're going from 0 is less than or equal to t, which is less than or equal to 1. So let's grab our graphing calculator. And I'm going to go ahead and clear out my old functions. And so we have x is equal to 3t, y is equal to 2 minus 2t, and let's go ahead and give that a quick graph. Now this is indeed a one that maps this, but however, you notice our range is restricted here. We're going from 0 to 1. So let's go ahead and just adjust our window here. I'm going to change this, our t-min to t-max to 1. And let's just go ahead then and regraph it. And you can see now we have this real tiny thing here. So I'm just going to go ahead and do a zoom fit here so you can see that a little bit nicer. You can see how that graph actually shows up. I'm going to adjust my t-step. Let's make that about, how about we do 0.25. And let's change our x values, make a max out here at about 5. And we'll do a y max. We'll also do 5. Just to kind of clean things up here a little bit nicer here. All right, and so this is a very nice looking graph here. And so now that we have that identified here, if we were to draw this, we of course could replicate this very easily and identify the different components of our graph here. So this gives us our graph. So if I hit trace, we can see we are starting at x is 0, y equals 2. And so that is our first endpoint. So let's go ahead and make sure we log that in here. So we have 0, 2 as our first endpoint. And what is our second endpoint? So if we trace that through, nope, we have another endpoint right here where we're ending right here because t equals 1. So we're having the point 3 and 0. So let's go ahead and log that endpoint. Now, of course, we need to figure out the parametric curve, which is tracing that segment of the line. And if we go again and look at this line, this is the little segment we want to kind of figure out here. The easiest way to approach this is to kind of do a little bit of substitution. If we look back at our y, we have y equals 2 minus 2t. Well, we also know that x is equal to 3t. And if I were to rewrite that in x in terms of t, I know that t is equal to x over 3. So if I plug the x over 3 into my y equation, so y equals 2 minus 2 times x over 3, I should find that y is then equal to 2 minus 2/3 x. And this is, of course, a pretty easy to rewrite into slope-intercept form. So we'll make this just a negative 2/3 x plus 2. And this, of course, would give us the equation that is mapping with our initial point starting at 0, 2 and our terminal point at 3, 0. All right, last one, which is going to parameterize a line segment. Now we have a line segment which has points negative 2, 1 and 3, 5. So what we need to do is create the parametric equation that's going to work for these points. I think we're going to pick negative 2, 1 because that's as good a point as any. So let's go ahead and create our x equation. So x equals, and if we look at our equation up here, we have a -2. So it's a -2. And since this is a line segment, I can just go ahead and just assume we're going to have some a value to go with t. And for my y, it's going to be something similar. We have a 1 plus some b value times t. So if I want to represent a line that could pass through these to create this line segment, the best thing I'm going to want to do is solve the equations for t and then kind of set them easier. So if we take this x equation, let's go ahead and solve that one for t. We can, of course, add 2 to both sides and divide by a. So I get x plus 2 over a is equal to t. And if I do the same thing here, I'm going to minus 1 and divide by b. So y minus 1 over b is equal to t. And since I know these both equal t now, I can set these two equations equal to one another. So then I would end up with x plus 2 over a is equal to y minus 1 over b. So now we know that this line, the equation that we have here, can pass through the point -2, 1 when we set t equal to 0. And we've determined a and b, so we also know now, well, can we go through 3, 5 when t equals 1? Because remember, with linear, it's typically going to be 0 is less than or equal to t, which is less than or equal to 1. So let's just do some quick math here. So if we take our second point, 3, 5, and start plugging it in, all right, we have our x value here. So we have 3 is equal to -2 plus a. All right, this should help us figure out what that is. Because remember, we're plugging in 1 here for t. So t in this point right now, we're having it equal 1. So this is the same thing as just saying times 1. So if I go ahead and work through this, we get 3 equals -2a, which means, plus a, there we go, means that a has to equal 5. And if we want to solve for b, we can grab our b coordinate, which is 5. We're going to do the exact same approach. Again, t equals 1. And we're going to say that 5 is equal to 1 plus b times 1. Again, that's just going to be 1 there. So if we work through this again, same process. We're going to say that 5 is equal to 1 plus b. So b has to equal 4. And now that we, of course, can verify this, we have our a and we have our b. We can then assemble our final version of these equations up here. Because remember before, we didn't know a, we didn't know b. So let's go ahead and put that all together. I'm going to then go ahead and rewrite these so I can get my parameterization. And that's going to be x equals -2 plus, and we said a was 5, so we can go ahead and pull that out, so it's 5t. And our second line is y equals 1 plus 4, because that's what we got here, t. And for both of these equations, this is going to happen from 0 is less than or equal to t, which is less than or equal to 1. And so that gives us our parameterization of line segment with our initial, this is our initial point, -2, 1, and our terminal point, 3, 5.